In the next two sections, we're actually going to explore a new computational technique. We've gotten a lot of theory, but really when it comes to computing, it's all pretty much been row reduction, row reduction, row reduction. So we're finally going to get a second computational tool here, namely the idea of the inverse. So let's talk about the inverse matrix. And as we get started on that, I just want you to recall the idea of an inverse just in basic equation solving. So maybe you have an equation like 5x equals 10, and because you all are mathematical superstars, of course you immediately see the solution to this is 2, and you probably don't even think about the steps that you are taking. But just let me remind you that really what you're doing is multiplying both sides by 1/5. Or maybe you thought of it as dividing by 5, but excuse me, but the same thing. And even here, probably the next thing you want to write down is x equals 2, because you can do these multiplications in your head. But let me be really explicit and say what's going on here is that 1/5 times 5 doesn't just cancel. I mean, it doesn't cancel. That's not the technical thing that happens here, right? 1/5 times 5 is 1. So the intermediate step that no one ever writes down, and 1/5 times, well, I'll go ahead and do that multiplication. 1/5 times 10 is 2. But the intermediate step no one ever writes down is this one, that 1x equals 2. And the reason why no one ever writes that down is we know that 1 times anything in multiplicative identity, 1 times anything is just that thing. And that's the whole reason why you chose 1/5, right? It's because 1/5 times 5 would make 1, and 1 times that thing would be just that thing, and then you would know that that thing happens to be 2. Okay, fair enough. So I should just point out that 1/5 is the inverse, the multiplicative inverse, if you want to get fancy. And it turns out, now that we know how to multiply matrices, that there is a matrix inverse as well. So let's take a look at one example. So now what we're getting when we do matrix equations, of course, is instead of having 5x equals 10, we'll have something more like an ax equals b. So suppose our A matrix here is 4, 11, 5, or sort 4, 9, 5, 11. And I'm going to try to solve this system, this matrix system down here, not by row reduction, but by this inverse, multiplying by the inverse technique, which should allow me to solve for x. So the first question is, can we even find out what A inverse is? The notation for A inverse looks like this. Kind of matches the notation for 5 and 1/5, right? Because 1/5 is also 5 to the negative 1 power. That could be written like that. And keep in mind, we want something that we can multiply times A and get the matrix equivalent of 1. The multiplicative identity. So what we really want to produce here is the 2 by 2 identity matrix. This is the one that will give you, 1 of the first column in the first column and 1 of the second column in the second column, right? This is the identity that you can multiply 1 or the identity times a matrix and just get the matrix or the vector. Okay, so anyway, all that to say, that's what we're trying to produce. Is just some little 2 by 2 matrix here that when I multiply it by A, I get 1, 0, 0, 1. So let me just pull something out of my hat. And let's see if this really is the inverse matrix. Let's multiply these two together. So keep in mind we've got two ways we can do matrix multiplication. We can either do add a couple columns together, and then add a couple columns together again, or we can do the row by column matching up. And I think I'm going to do the row by column matching up version this time around. So let's see if we can verify that that 1 is correct. First row, first column. So first row by first column. That would be negative 44, and 9 times 5 is 45. So negative 44 plus 45 is indeed 1. Let's do first row, second column. So the 4 and the 9 with the negative 9 and 4. I think you can see that's going to work. That'll be 36 minus 36. So that's 0. 5 times negative 11 and 11 times 5 added up. Those are 0. That one works. And this is 45 minus 44. So that makes 1. So at least for this particular A, we have the A inverse. And if we had a system down here that looked like 4, 9, 5, 11 times an unknown, and it equaled like whatever, 2, 8. Again, we could do augmented matrix and row reduce, but now we have a second technique. We could multiply both sides by the inverse. So the inverse I know to be negative 11, 9, 5, negative 4. And of course, if I multiply one side of the equation by it, I need to multiply the other side of the equation by it. Remind yourself that matrix multiplication is not commutative. Order matters here. So if you multiplied the left-hand side of the equation on the left, you should multiply the right-hand side of the equation on the left as well. So I'm putting the negative 11, 9, 5, negative 4 on the left side of both parts of this equation. I did the same thing up here with the 1/5. It doesn't matter, of course, because normal numeric multiplication is commutative, and the 1/5 could have been to the right of the 10, but I was careful to put it on the left both times, just in preparation for the importance of doing that down here. Okay, let me point out, since we've already done it, that this multiplication right here turns into the identity. This multiplication right here I need to actually work out, and let's see, that would be, this time I'll do adding vectors version of matrix multiplication. It would be 2 of the first column plus 8 of the second column, and I'll finish that out in a second. But let me just point out that we're essentially on this step right now. We've got 1 times x, and again, we don't normally even write that step down. We just typically jump straight to the fact that we just have x over here. It is true, if you want to multiply this out, that multiplying 1, 0, 0, 1 times x1, x2 does just make x1, x2. And on this side, I need to do a little bit of number crunching. Let's see, the top is going to be negative 22, and 9 times 8 is 72, minus 22. I should have practiced this beforehand. 50, right, I think. 50, and on the bottom, 10 minus 32, so negative 22. If I made a mistake, let me know. But hopefully you get the idea anyway, and I think hopefully I got the right numbers there. So ta-da, we now have a second way to solve a system of linear equations by finding this inverse. And of course, I'll say if you're just solving one system of linear equations, probably the inverse is not the most efficient way to do it, because first you have to find the inverse, then you have to multiply, which I think finding the inverse, which we don't even know how to do yet, and then multiplying by the inverse is more work than just row reducing. The inverse can be really useful when you're solving this system over and over and over and over and over again, because once you have the inverse, then just multiplying by the inverse is less work than row reducing every time. So in the next video, we'll take a look at how to find an inverse in general. For this video, I want to just point out that there's kind of a one-trick pony that only works for the inverse of 2 by 2's. It doesn't work for anything bigger. But let's go ahead and take a look at that one-trick pony. This is Theorem 4. It says if you've got a 2 by 2 matrix, A, B, C, D, then the matrix is invertible as long as AD minus BC is not 0. If that's the case, it won't be invertible. But in any case, if it is invertible, you can use this little one-trick pony formula right here. This formula, by the way, is one that I have memorized because I'm a math super stud, but we're going to get a more general way to find inverses. And whether or not you choose to memorize this particular one, I would say is up to you. Okay, so let's take a look at how that worked for this 4, 11, 5, 9. The formula here says if you've got A, B, C, D, if you've got those, then the inverse should be 1 over AD minus BC. So let's look at that. The product this way, 4 times 11 is 44, minus 45. So 1 over negative 1 in this case. And then the rest of the inverse should be swap the main diagonal. So 4 and 11 go to 11, 4. And just change the sign on the off diagonal. So don't move the B and C, just change their signs. So negative 9, negative 5, and of course I simplified that before I wrote it down here because 1 over negative 1, that's a scalar multiplication of just negative 1, which multiplies every entry inside here. And there's our inverse for this particular matrix. Notice this is my opening example, so I was trying to keep things in whole numbers. It's entirely possible that AD minus BC is not 1 or negative 1, in which case you're multiplying through by a fraction. And a lot of times inverses involve fractions, which is no big shock if you think back to our algebra days. Kind of if you start with a whole number, it's typically going to be a fraction for the inverse, right? This is true for matrices as well. So a lot of times the inverse doesn't come out quite as clean as this one, but it's just numbers, right? We can handle fractions. So in the next video, we'll look at a more general way to find inverses for any matrix.